EDX Core Pure, Matrices 4, Determinants and Inverses of 3x3 matrices, the determinant of a 3x3 matrix. We've already looked at the determinant of a 2x2 matrix, and we've seen that the determinant of the matrix can be written as AD minus BC. If we consider this new notation for the matrix, we can write A as columns A1, A2 and B1, B2. Then the determinant of this matrix would become A1, B2 minus A2, B1. Calculating the determinant of a 3x3 matrix. The determinant of a 3x3 matrix can be found from the cofactors of any row or column of the matrix. Each element in that row or column is multiplied by its cofactor and the results are added together. For example, the determinant of a 3x3 matrix can be found by the first column using the determinant of A is the element A1 times its cofactor capital A1 plus element A2 times its cofactor capital A2 plus A3 times A3. This would be called expanding by the first column. So for this given 3x3 matrix with the cofactors that we can see there from capital A1 all the way to capital C3, a similar formula can be applied to any row or column of the matrix. So the determinant of A could be done as the first element A1 times its cofactor plus the next element across B1 times its cofactor times the third element across little c1 times its cofactor. So in this example, I'm going to expand the determinant by the first column. These three diagrams here are just to assist with the method. With practice, you would be able to find these determinants without having to draw the diagram. So these are just visual aids. So I'm going to expand by the first column. So I take the first element 5, cross out that row and that column. So I'm going to have the determinant is the element 5 times its cofactor. So its cofactor is the determinant of 2, 3, minus 1, 4, and because of its position in the matrix, it's been assigned with a plus sign. So now if we move on to the next element, which is the minus 3, so we're going to have the element minus 3, and we need to multiply by its cofactor. So first we find its minor, so we lose the row and the column, and the determinant that's left is 1 minus 1 minus 2, 4. But because of its position in the matrix, it's been assigned with a minus, so it's going to be minus 3 times the minor. If we move on to the third element in the column, so that's an 8, so we cross out that row and that column. So now we have 8, and we need to find its minor, so that's going to be the determinant of 1, 2, minus 2, 3. And because of its position in the matrix, this one has been assigned with a plus sign. So we've got 5 times its minor, minus 3 times the minor, plus 8 times the minor. So this minor is 8 minus 3, which is 11. This one is 4 minus 2, so that's a 2, and this one is 3 minus 4, which is 7. So we've got 55 plus 6 plus 56, which is 117, is the determinant of that 3x3 matrix. And we can see the full method there. You can also see that you don't need those 3 extra diagrams. They were just there as a visual aid to help us to see the method. You can expand any 3 by 3 matrix along any row or column. So here I'm going to expand it along the third row, and again I'm going to use these three diagrams as a visual aid. So taking the first element 8, so that'll be a positive 8 due to its position in the matrix times its minor 1, minus 2, 2, 3. Taking the next element across, minus 1, due to its position in the matrix this will be a minus 1 times its minor, which would be 5 minus 3 minus 2, 3. And then moving across to the last element, that's a 4, and due to its position in the matrix it's a plus 4 times its own minor, 5 minus 3, 1, 2. So that's 8 times its minor, minus 1 times its minor, plus 4 times its minor. So this determinant is 3 minus 4, which is 7. This one is 15 minus 6, which is 9. And here we have 10 minus 3, which is 13. So we've got 56 plus 9 plus 52, which is 117 again. So whichever row or column you decide to find the determinant along, the expansion of the determinant will always simplify down to that expression. I wouldn't recommend learning that expression. I would stick to the method that we've looked at previously, but they all boil down to the same algebraic expression. So the determinant is the same no matter which row or column is used for the calculation. However, you can save working and time by choosing a row or column carefully. If, for example, one of the elements in the column or row was 0, there would be no need to calculate the cofactor for that element. So if possible, you should choose a row or a column which contains one or more zeros. So you can see in this example we need the determinant of n, and the expansion can be simplified if we expand along the second row. So we've taken advantage of this 0. So the determinant is simply 0, then a 3 times its minor, and then minus 1 times its minor. Notice the minus 1 because of its position in the matrix. So that has reduced the amount of calculations needed because this first calculation is obviously 0. So now we can see some similarity between the determinants of an n by n matrix. So the determinant of a 2 by 2 matrix was a1 b2 minus a2 b1, and the determinant of a 3 by 3 matrix was the expression, algebraic expression that we've just been considering. So for a 4 by 4 matrix you'd need to find the 4 cofactors, each of which would involve the determinant of a 3 by 3 matrix, which would be a really long-winded method and far too complex to do by hand or in an exam. It's worth noting that the determinant of a 1 by 1 matrix, which is obviously a very trivial case, would just be a single value. So in this example we want to show that x equals 2 is one of the roots of the equation the determinant equals 0, and we've got to find the other roots. So we could check that x equals 2 simply by replacing the x with a 2 and checking that the determinant is 0. So I'm going to do it a slightly different way. I'm going to do this determinant algebraically and see if we end up with the answer x equals 2. I'm going to take advantage of this 0 in the bottom row, and I'm going to expand by the bottom row. So I need the first element x times its minor, which would be 1x x 3, and that would be a positive x due to its position in the matrix. Then I'd move on to 2, and its minor would be 1, 2 x 3, and due to its position in the matrix that would be assigned a negative, and then I can move on to the 0 and simply put 0. So we've got x times its minor minus 2 times its minor is 0. So this minor is 3 minus x squared, and this one is 3 minus 2x. So expanding the brackets, we get 3x minus x cubed minus 6 plus 4x is 0. And if we rearrange it, we can get it in the more helpful form of x cubed minus 7x plus 6 is 0. So now we're trying to show that x equals 2 is a root of this far more familiar equation. So it would be sensible to think about doing perhaps a factor theorem. F of 2 would be 2 cubed minus 2 sevens plus 6, which is definitely 0. Therefore we conclude that x equals 2 is definitely one of the roots. Now we need to find the other roots of this cubic. So if we take the cubic again, x cubed minus 7x plus 6 equals 0. We know that one of the factors is now x minus 2, and we need to find the missing quadratic factor. We could do that by long division or a box method. I'm going to use an inspection method, so I'm going to say to get the x cubed I need x times x squared. So now here we have minus 2x squared where there are no x squareds in the polynomial. So I need an extra 2x squared, and that comes from this x times plus 2x. Now I've made a minus 4x when there's supposed to be minus 7x, so I need another minus 3x, and that comes from x times minus 3. And the nice thing about this method is it checks itself at the end. Minus 2 times minus 3 is 6. So now we've got x minus 2. The quadratic will factorise to x minus 1, x plus 3, and the three roots of the original equation are x equals 2, x equals 1, x equals minus 3. So in the next session we're going to be looking at the inverse of a 3 by 3 matrix.